Welcome to our today's lesson, and today we are going to plot the bending moment diagram as well as the shear force diagram for this continuous beam that we are given here. It is supported on three supports, support A, B as well as support C, and we are going to use the moment distribution method to plot the bending moment diagram. And in our previous lesson, or in our previous video, we looked at the steps that are going to guide you when you are applying the moment distribution method. And please, ladies and gentlemen, if you are here to subscribe, please consider hitting that subscription button. We are going to begin with the calculation of the fixed end moments, and in this case we are going to begin with the span A to B. Now, on the span A to B, the fixed end moment at A will be given by this formula: negative W AB squared divided by L1 squared, which in this case W is the point load at D, 3 kilonewtons, so we got negative 3 kilonewtons multiplied by A, that is the span A to D, which is 2 meters, multiplied by B, that is the span D to B, which is 4 meters, and then we square it. Then we divide this by the overall span A to B, which is 6 meters, and then we square that 6. So when we do so, this is going to give us a fixed end moment of negative 2.67 kilonewton meter. The negative, since the moment at the end A is going to be an anti-clockwise moment, and in this case anti-clockwise moments will be represented by negative sign. Then from there, the fixed end moment at B, still in the span AB, will be given by positive W A squared B divided by L squared. So you will find that when we are calculating the fixed moment at A, we are squaring B. When we are calculating the fixed end moment at B, we are squaring A. So that is a difference that should be noted very clearly. And this is going to give us positive 3 multiplied by 2 squared, which is A, multiplied by 4. Then we divide this by 6. And when we do so, we are going to get a fixed moment at B of 1.33 kilonewton meter. So that is in the span A to B. Then this positive means that the moment, fixed end moment at B is going to be a clockwise moment. Then we go to the span B to C. Therefore, in span BC, in the span BC, the fixed end moment at B, in this case, is going to be an anti-clockwise moment, which will be given by this formula: negative W L1 L2 squared divided by 12, since the span BC is loaded with a uniformly distributed load. And in this case, W is 1 kilonewtons per meter. Therefore, we are going to have negative 1 multiplied by L2, which is 4 squared, and then we divide this by 12. And when we do that, we are going to get the fixed end moment at B being equal to negative 1.33 kilonewton meter. So we go to the fixed end moment at C, which is going to be a clockwise moment, and it will be given by this formula. Therefore, fixed end moment at C is going to be positive WL2 squared divided by 12, which is going to be positive 1 times 4 squared, divide this by 12. And when we do so, we are going to get a fixed end moment at C of 1.33 kilonewton meter. After determining the fixed end moments on both spans, the next thing we are going to determine is the stiffness factors. So we go to stiffness factors. And in this case, we are going to begin with the span BA. So for the span BA, the stiffness factor, that is KBA, will be given by 3EI divided by L. Since the beam is hinged at A, or in other words, the beam is simply supported at A. So when a beam is simply supported or hinged, the stiffness factor is usually given by this formula, whereby E is the modulus of elasticity, I is the moment of inertia, and L is the span A to B. So in this case, we are going to have L1. This is going to be equal to 3EI divided by L1, which is 6. And when you simplify that, that is going to give us a stiffness factor of a half EI. Then the stiffness factor on the member BC, that is KBC, will also be given by 3EI divided by L2, since the beam is also hinged at C, or it is simply supported at C. And this is going to give us 3EI divided by L2, which is 4 meters. So that is KBC. Now, summation of the stiffness factor, that is summation of K. It is going to be a half EI. So we are going to have a half EI plus 3 over 4 EI. The reason as to why we need the summation of the stiffness factor is because we are going to use it when we are determining the distribution factors. And this is going to give us an LCM of 4. So this is going to be 2EI plus 3EI, which is going to give us a total stiffness factor of, that is summation of K. Summation of K is going to be 5EI divided by 4. Then after that, we are going to determine what we call the distribution factors. So we go to distribution factors. And for the distribution factors, we are going to begin with the distribution factor on the member BA. So this is going to be distribution factor on the member BA, and it is going to be given by the stiffness factor on the member BA divided by the summation of the stiffness factor. So this is going to be KBA, which is a half of EI. So you got a half EI divided by summation of the stiffness factor, that is 5EI divided by 4. So you got 5EI divided by 4. This is going to give us a distribution factor on the member BA of a half EI multiplied by 4 over 5 EI. The EI and EI are going to cancel out by 2, 1 by 2, 2. So we are going to get a distribution factor of 2 over 5. And therefore, that is the distribution factor on the member BA. From there, we go to distribution factor on the member BC. So on the member BC, this is going to be given by stiffness factor on the member BC divided by the summation of the stiffness factors, which will be equal to KBC. We got it as 3 over 4 EI. So this is going to be 3 over 4 EI divided by summation of stiffness factors, that is 5 EI all over 4. And this is going to give us a distribution factor on the member BC, which will be 3 over 4 EI times 4 over 5 EI. So the EI and the EI are going to cancel out. 4 and 4 are going to cancel out, and we are going to have a distribution factor on the member BC of 3 over 5. So after getting the distribution factors, the next thing will now be taking all these values to our distribution table, and then we carry out the distribution. So this is how our distribution table is going to look like. We are going to have joints, and in this case we have 3 joints: joint A, joint B, as well as joint C. And when you are talking about the joints, it is where we got the supports. So you have joint A, joint B, as well as joint C. On the joint A, we got the member A to B, which is that. So those are the spans. We got the span A to B. On the joint B, we got 2 spans. We got the span BA as well as the span BC. On the joint C, we are going to have the span C to B. Then the distribution factors on the span B to A, the distribution factor is 2 over 5. On the member BC, on the member B to C, the distribution factor is 3 over 5. Then after that, we have the fixed end moments. So on the span AB, the fixed end moment at A is negative 2.67, and on the joint B, the fixed end moment is 1.33, which is positive a clockwise fixed end moment. Then in the span BC, the fixed end moment at B is an anti-clockwise moment of negative 1.33 kilonewtons meter, which I have written there. And then on the joint C, we are going to have a clockwise fixed end moment of positive 1.33 kilonewtons meter, which is at that point. Our next step is going to be release, A and C. And when we are releasing, we usually release with an equal and opposite moment. So on the joint A, we are going to release by positive 2.67, and on the joint C, we are going to release by a moment of negative 1.33 kilonewtons meter. So you just change the sign. So that is what we usually do when we got both the end joints being simply supported. Then after we have released A and C, we are going to carry over half of this moment to the joint B on the left hand side, and we on the span BC, we are going to carry half of this moment on the joint B, that is on the span B to C. So, and we said in our previous lesson that the carryover factor is always a half. So we are going to carry half of this moment to the joint B, and half of 2.67 is 1.33. So we are going to have positive 1.33. Then we do the same on this side. We carry half of this moment on joint B, but on the span B to C. And half of 1.33 is 0.67. So we are going to have negative 0.67. And then from there, we are going now to have the initial moments. So after cutting over, you are now going to have the initial moments. Initial moments. The joint A on the span AB, we are going to add these two moments, which will give us a 0. Then on the joint B, on the span B to A, we are going to add these two, which are going to give us 2.66. So here we have positive 2.66. On the span BC, still on joint B, we are going to add these two, that is negative 1.33 minus, that is plus negative 0.67, which is going to give us negative 2.00. Then on the joint C, we are going to have 1.33 minus 1.33, which is 0. Then after that, we are going to distribute. Here we have an excess moment of 0.66. So the next thing we are going to do is to distribute. So we distribute, and this is what we are going to have. We have an excess moment of 0.66, and what we usually do for us to get the excess moment, we usually change side. So for the positive 2.66, we are going to take it as negative 2.66, and for negative 2.00, it is going to be positive 2.00, and that is going to give us an excess moment of negative 0.66. So what we are going to do, we are going to distribute this excess moment of negative 0.66 on the joint B on the left hand side by the distribution factor of 2 over 5. So we are going to have this 2 over 5, 2/5 of negative 0.66, and that is going to give us negative 0.26. Then on the span BC, we are going to do the same. We distribute this excess moment with this distribution factor on the span BC. So that is going to be 3 over 5 multiplied by negative 0.66, and that is going to give us negative 0.40. So when we distribute on this side, we are going to have negative 0.26, and on this side we are going to have negative 0.40. So that is going to be 0, and on the other side we are going to have 0. After distributing, we are going to have final moments. And for us to get the final moments, we are going to add the initial moments plus what we have distributed. So on the span AB, on the joint A, we are going to have 0, 0 plus 0, that is 0. And the span BC on joint B, we are going to have 2.66 minus 0.26, which is positive 2.40. And on this side again, minus 2 minus 0.40, that is minus 2.40. And we are going to have a 0 there. Let's calculate the maximum bending moments at D, that is in the span AB, as well as the maximum bending moment on the span BC. So we go to maximum bending moments due to vertical loads. Bending moments due to vertical loads. And in this case, so we are going to begin with the span AB. And for the span AB, we are going to determine the bending moment at D, and the bending moment at D will be given by WAB divided by L. So that is the formula of calculating the bending moment at D. WAB divided by L1. So let's have here is L1, and in this case W is 3 kilonewtons, A is A to D 2 meters, B is D to B, which is 4 meters, divided by L1, which is 6 meters. And that is going to give us a bending moment of 4 kilonewtons meter. So that is the bending moment at D. Then on the span BC, so for span B to C, the maximum bending moment, since that span is loaded with a UDL, will be given by WL2 squared divided by 8. And that is going to be equal to W is 1, L2 is 4 meters, therefore 4 squared divided by 8. And that is going to give us a maximum bending moment of 2 kilonewtons meter. So that's what we got. Then after that, we can now plot the bending moment diagram. Let's begin with the bending moments due to vertical loads. And on the span AB, we got the bending moment at D, which is 4 kilonewtons meter. So let's have it at this point. So we are going to join these two, bending moment at A, and then we join it to B as well. So that's what we got. Then on the span BC, it is a UDL, so it is going to be a smooth curve of 2 kilonewtons per meter. So we plot a smooth curve whose value is 2 kilonewtons per meter. And I guess that is quite a smooth curve. So this is 2 kNm. Then the bending moment due to the support B, we got it as 2.40, just few units above 2. So let's have it at that point. And we are going to join that to A as well as to C. And this is going to be 2.40 kilonewton meter. And this is going to be a positive bending moment, this is going to be a negative bending moment, and this one a positive bending moment. And now to complete our bending moment diagram, we are going to shade off its outline so that it becomes clear and visible. And so guys, that's how we usually plot the bending moment diagram for such a continuous beam using the moment distribution method.